Excellent. Thank you so much. I am a new postdoc at the Lunar and Planetary Institute, and I'm excited to talk about my ordinary chondrite project. In particular, today I'll focus in on the L/LLs, or the triple Ls. So next slide, please. The introduction we just received for asteroid-meteorite linkages was excellent, led me right in. The linkages that have been established for the roughly 80,000 terrestrial meteorites largely lived within the HED clan and asteroid Vesta. This was first done with ground-based telescope observations from McGraw et al. 1970. The return of the Apollo and Luna samples made us realize, of course, that we already had lunar samples within the meteorite collection. And of course, those gases trapped in the Martian meteorites aligned with the planet Mars. For the ordinary chondrites, a very strong linkage lives within the Itokawa and the LL ordinary chondrites. Also mentioned, the Flora asteroid family has a strong linkage within the LLs. But these LL chondrites only make up about 10 to 11% of the total meteorite collection. But yet Greenwood et al. 2020 suggests that given our entire meteorite collection, there should be something on the order of 96 to 148 parent bodies represented completely what we already have here. And the ordinary chondrites make up this large category, 86% of what makes it down to our collection. But few linkages actually exist for the true parent bodies. The ordinary chondrites within that Greenwood et al. Geochemistry argues that there should be about 30 parent bodies for the entire ordinary chondrite representation. And my PhD thesis was to test the hypothesis if the Gefion asteroid family is responsible for the L chondrite linkages. And this was in the research family tree, as aforementioned, in this asteroid meteorite linkages following on from Gaffey. The L chondrites have this very interesting component that during the Middle Ordovician, 467 million years ago, for a couple million years, there's a higher flux, roughly 1,000 times the meteorites flux that you would see on the average night to night was thought to infall, and that's given within that Ordovician sediments. And of course, you could see these fossil meteorites right next to these shelly creatures in the photo in the bottom right here. Next slide, please. So the Weisberg et al. 2006 chart is a little bit of an eye chart, but of course the way in which we can organize the undifferentiated chondrites, primitive achondrites, and differentiated achondrites. I'm focusing on the ordinary chondrites and more particularly what I am calling the unordinary chondrites. So we're going to have 3 clicks here. So click advance one more. Down below the ordinary chondrites on the left side of the screen, I have the proposed either maybe a new group or perhaps a subgroup within that I've called the H/Ls and the L/LLs. And this has also been identified within the meteoritical bulletin. If you click one more, there are 130 accepted specimens currently in the meteoritical bulletin for the L/LLs. Similarly, there is a category for the H/Ls, but for this component of the project today, I want to focus on these triple Ls, which I have a triple L shown here in the top right of the figure. And additionally, many LLs or Ls are being recategorized. For instance, one famous meteorite is the Holbrook meteorite, which hit in northern Arizona, and it's now a triple L as well. Next slide, please. And I will have I believe it's 5 clicks here, so you can just slowly click forward. So using infrared spectroscopy, we can identify mafic mineralogy to identify these broad crystal field absorption features, olivine being the identifier near 1 micron with this large absorption feature. This is the San Carlos olivine, which I was able to collect out in the field, and pyroxene being the other large, most dominant mafic mineral that we see in the ordinary chondrites, with 2 identifiers. If you look along that x-axis, the wavelength and micrometer space, we can see 2 large features, one near 1 micron due to both olivine and pyroxene, and near 2 microns for pyroxene. And so can these be used to better identify and tease out some of the regions within the ordinary contract? So if we hit next, I think there's going to be another click. So these are used to contain those relative abundances. And one more. Next slide. Okay, so when I use this infrared spectroscopy to measure Gefion asteroid targets, we could see the main band parameters listed here, which again, Tasha Dunn gave a great intro for us. Again, here's the olivine and pyroxene with those main identifiers and those band centers. And so this is what I'll use to identify the mineralogy. Next slide. And so out of my PhD thesis, I had really good spectra in total for about 18 Gefion asteroid targets, even though I started out with 50. And if you hit one more, we're going to see the error bars pop up. So within these regions, these are the error bars within my data. And given the spread, this is the Nakamura et al. Plot with these laboratory measurements for ordinary chondrites. And on top of them are my Gefion asteroid targets. The error given those spectral, my targets, the spectra of my asteroid targets, I could consider that, let's take, say, the top purple triangle, asteroid 44528, which is just on the bounds of the L/LL region. Consider the error. Considering the error, I could call this an L chondrite, I could call this an LL chondrite, and then also that in this new category, that there's actually a triple L category. And so this started making me scratch my head and think there's probably something that I could tease out. How could I be sure that the error within my spectra is really, you know, perhaps linking to these meteorites? And so on the next slide, oh, sorry, I forgot. There's the bar. I want to focus in on samples within this region. I want to use laboratory samples, return samples that are perhaps in this region to really help identify the iron content, to better inform my spectra. Next slide. Oh, sorry, the error bars again. One more. So this leads me to the Itokawa samples. And so I've identified two main samples that I'd like to use for my investigation for these triple L research. One that is olivine and rich in troilite, the sample here on the left with the coded name that I will just call 84. It's 100 microns wide. And I would also like to focus on a sample that is predominantly purely olivine, and that is sample 215 listed on the right, and it's 31 microns wide. Next slide, please. The olivine troilite, I chose this as it has iron both in the olivine and in the FES, the iron sulfide. And I want to quantify the iron first from the EDS spectra. I don't think I necessarily even need the sample in hand. If I can just get the EDS spectra, this will help determine some of the iron content in the olivine and the troilite. And then I want to use this iron to inform what I call my mini-me model, which I'll introduce. Next slide. The olivine similarly as the same exact steps, and these are my two main desired samples from Itokawa. Next slide. Mini-me, this is an eye chart that I made especially for you all. Okay, so we don't have to go through the whole thing, but I am by design a planetary astronomer geologist, and so it's time to use observational data to better inform a model, which can then better inform what's actually in the spectra. And so I hope to use a me scattering model, which has parameters such as the size of the wavelength coming in and the incident angle of that wavelength coming in, which also is fed in by the mineral that I'm actually investigating, which has porosity components, the rock matrix that it is, and particularly the nanophase iron. This also includes a refractive index for that particular mineral, as well as some particle shapes. I've heard some mention that Itokawa samples are both angular and some rounded, and I would be really curious to learn more about that because they all look angular to me. But essentially, this mini-me model, the mineral investigation with me scattering, is going to give me a scattering cross-section, which will give me the scattering matrix, which will tell me how the light is interacting with the particles at different angles, and how this is contributing to that diffuse reflectance. I can then hopefully simulate effects of the nanophase iron, both for the meteorite and asteroid reflectance, and that this will be done within the 0.7 to 2.5 micron range. I then hope that this can grow to adjust the amount of nanophase iron. If I can quantify how much iron in a spectra is due to nanophase iron or truly within the minerals, perhaps this can help estimate for the surface of the asteroid spectra. I have mainly that I want to do this with an olivine-rich basalt, which is my collected terrestrial olivine, which I already have. Of course, the Apollo sample I have identified, that's a lunar-rich regolith, and of course, those wonderful Itokawa samples to get the surface of that asteroid, at least the EDS spectra. Next slide.
Oh, and you have 5 minutes.
Thank you. So this is the showcase of my main samples that I would like to use starting out with this project. I already own several L/LLs. I identified this at the tail end of my PhD thesis, and I started purchasing as many triple L's as I could. So I own several, and my goal is to own a haul 130, because hey, that's a low collection to own. Of course, those samples from Itokawa, if I could get at least the EDS spectra is a great starting point. The San Carlos olivine, and then lunar sample I've identified as very olivine rich regolith, lunar sample 76035. Next slide. I'll also use the SEM and continue my FTIR work here at the Lunar and Planetary Institute in my new institution. And this is a first look and first pass that I was able to use for triple L Bijaburle, which is a triple L that fell into the bottom of a lake that somebody recovered. Thank you, meteorite hunters. Next slide. So just an overall, I hope to obtain elemental data, really focusing on iron, and mineral data for meteorites within that triple L. I hope to actually get some more published research. There's not any true papers that address the triple L's quite yet, since it's again, they're showing up in the meteorological bulletin, but I hope to get some wholesome look research papers, use the Hayabusa samples to better constrain the iron content for the triple or for the LLs, which leads into identifying if this triple L truly has a separate parent body within that Greenwood et al. Geochemistry. Perhaps there's a couple triple L parent bodies. And help to use this mini-me model to help inform the nanophase iron using those Hayabusa and starting with Apollo samples. And then applying this nanophase iron ordinary chondrite knowledge to create these stronger asteroid meteorite linkages. And I meant to leave myself 3 minutes for questions, and I think I have 2. I'll take anything or in the chat too. Thank you.
Thanks so much, Allison. I don't see questions in chat yet. I have a question. So I wonder how the dedication of parent families reflects on your LLL combination there. If must be then some asteroid family that's providing these, and where how that might confuse the issue of where the L's and LLs are derived from.
Yes, and one issue is just the amount of, this is not the scope to talk about Gefion per se, but many interlopers within the Gefion asteroid family. And not only that, the Gefion asteroid family was proposed to be a mixture of H and L's as well, and L's. And then also, like Tasha mentioned with our work for the Massalia family, which just came out last year, is that there's also, you know, there's multiple parent bodies, obviously, for different, or for say, even just the L chondrites, but mixing, and if there was any collisional mixing too, is much to tease out, definitely. But at the very least, there's at least a distinct category of the triple L's. So I'm inclined to think that they at least have one separate parent body of their own. I've not identified if all these triple L's are all perfectly related yet. It's about every couple months, a couple more show up on the meteorological bulletin.
Okay,
and
thank you,
I think
Allison.
Thank you. Thank you. I saw a question, I think, of my institution. Yes, I just started at LPI this week. And so, of course, we submitted our presentations. I uploaded last week. No matter what, I can always be reached at the arizona.edu. Thank you, Arizona. Let us keep our alumni email. But I'm also a McGraw at lpi.usra. But either one is
Okay.
fine.